All right, so with exponential growth and decay, so this is going to kind of build on what we did with attributes of exponential functions. So just to kind of refresh your memory, we're going to start with an attributes problem. So we want to identify the following attributes of the exponential function. So given the table here, we know that the 5 here, 0, 5, that's going to be your initial amount or your initial value. And so this is going to be your a value, which is 5. And now we want to find the common ratio. So we want to see how are we going to the next value. So to go from 5 to 10, or do 10 to 20. So to go from 5 to 10, 10 to 20, that's going to be times 2. So that means your common ratio here which is your b value, is going to be equal to 2. All right, so I'm going to kind of use this information to go ahead and start the problem. So for a growth or decay, the numbers are getting bigger, which is going to mean this is a growth. So you can either highlight or you can write it out. It's up to you. The initial value, which is going to be 5. The common ratio, which we said was 2, which means your equation is going to be y equals 5 parentheses 2 raised to the x. And then we want to use the equation to find f of 5. So I'm just going to plug in the calculator. So 5 parentheses 2 raised to the 5th, which is 160. Perfect. So we get 160. All right, and then your domain, as always, all real numbers, which hopefully you remember is your freebie. Then your range, all the numbers are positive, so it's y greater than 0, and then your asymptote, as always, is y equals 0. All right, so we're going to kind of use the exponential functions equation, so y equals a parentheses b raised to the x, and we're actually going to elaborate on the b value more. So this is really the applications of what we did in 10b. All right, so we are now looking at the equation y equals a parentheses 1 plus or minus r all raised to the t. So your different components, so your a value is going to represent the initial amount or the initial value. Your r value is going to represent a growth rate. So it's going to typically be given to you in terms of a percent, which means you will have to convert the percent to a decimal. And then t value is going to be given to you in terms of time. So it could be per day, per week, per year, per decade, per millennia, per century, per whatever. All right, so remember, we have two different types of exponential equations. We have a growth and a decay. So in a growth model, that's going to be using addition in the exponential growth and decay. Whereas a decay model is going to be using subtraction. So just that one little operation difference is going to make the world of difference in these equations. All right, so just to kind of start off, I give you these 5 problems and you just need to determine the a value, the growth rate, and determine if it is a growth or decay. All right, so looking here at number 1, looking at just the different little components that we have here. So we have our a value, which is 2, and then our growth rate right here, which is 0.45. All right, and because we are adding, that's going to tell us this is a growth. All right, so you have an a value of 2, an initial amount. Then we have an r value of 0.45. And we know because it's adding that it's going to be a growth. So there's the information for this question. All right, now looking at the next one, number 2. So it's written a little bit differently. So we know our a value is written outside, so we have a equals 100. All right, however, now if you look inside the parentheses here, notice it's not 1 plus or 1 minus, but notice how it's less than 1. So because it's less than 1, that automatically means it's going to be a decay. So we still need to find the R value. So I'm actually going to rewrite this equation as y equals 100 and then do 1 minus 0.25 so that it's kind of expanded and I can actually see what the growth rate is. So your growth rate is actually this 0.25 here. So your growth rate is 0.25. All right. And over here, number 3, same idea. So I'm going to go ahead and just rewrite my equation first. So I have y equals 175, 1 plus 0.05 raised to the t, because you actually want to be able to identify your growth rate. So that's why I'm going to go ahead and separate it out. So we have an initial amount of 175. We have a growth rate that is 0.05. And then because the equation's adding, that's going to tell you it is a growth. All right. So now we have a couple word problems here. So a couple applications. So there are approximately 250 rabbits in a population research study. The population is increasing at a rate of 7% each year. All right, so they tell you it's going to start off with a population of 250 rabbits. So what that means is 250 is your A value, and then the population is increasing. So because the population is increasing, that's going to be your indicator that this is a growth. And then because it's increasing at a rate of 7%, I'm going to convert that percent to a decimal by just moving that decimal value to the left twice. So we have an R value of 0.07. All right, so I have an A value of 250. We have a growth rate of 7%, which is 0.07. And because it's increasing, we know that this is going to be a growth. All right, now looking at the next one. So a new car is purchased for $35K, which is 35,000, and it depreciates in value by 20% every year. All right, so now for this question, it's purchased at 35K, which is $35,000. So this is going to be your A value, and it's going to depreciate. So when I say depreciate, depreciate means it's going to lose value. So because it's losing value, that implies that it's going to be a decay. All right. And it's losing its value of 20% every year. So that means we have an R value of 0.20, 20%. So once again, we have an initial amount of 35,000. Now you could write 35,000 as 35,000, or if you want, you could write 35K. Then we have a growth rate, which is depreciating at a rate of 20%. And because it's depreciating, that's going to tell us we have a decay. All right, so this is just kind of scraping the surface of exponential growth and decay. So now we're actually going to solve some of these applications. All right, so I will say a calculator is going to make these problems exponentially easier. So no pun intended. Calculator will make this so much easier. If you do this by hand, it's possible. It's just going to make your life a little bit more challenging. All right, so starting off in the year 2000, gold costs $1,500 per ounce. So the price of gold has been increasing by 15% per year. All right, so we want to determine, is this going to be a exponential growth or is it going to be an exponential decay? And then you also have to justify it. So keep in mind, it's increasing by 15%. So that's going to tell you it's going to be a growth. So the price is increasing. All right. So now you want to actually write an equation to estimate the price of gold in each year since the year 2000. All right, so remember, it's starting off at a price per ounce of 1,500. And the growth rate, so it's going to be increasing by 15% per year. Had to go back to the problem. So our growth rate is 0.15. And using this information, I actually want to write the equation. So I want to use the growth model. So I'm going to do y equals 1,500. Actually, let's do this. Start with the growth model. So y equals a parentheses, 1 plus r raised to the t. So I'm just starting off by writing the equation. So that means I'm going to plug in for both a and r. So I'm going to have y equals 1,500, 1 plus 0.15, and that's going to be raised to the t. So you could leave your equation like this with it expanded, or you could consolidate and rewrite it. It's up to you. It's not going to matter. I could technically give you both of the options on an assessment. I will say this one's going to be more widely accepted and more commonly seen, but just know that either of them are acceptable. All right, so now I actually want to find the value of gold in each of the following years. So keep in mind, this is starting in the year 2000. So this is if no time has passed. So your t value is 0. So that means what I'm going to be doing is plugging in 1.15 raised to the t. So if no time has passed, then that means I'm plugging to the 0 power, which is literally just going to be the initial amount of 1,500. Let's do this better. All right. So now we want to find the cost of gold after, or in the year 2005. So in the year 2005, that's 5 years after the original date, which means now I want to find I'm going to replace that t value with 5, and that's what I want to find. So when I find this value, that's going to give you approximately, so let's do this. This is going to be 3,017.035,781. Now keep in mind, we're dealing with money here. We can only round to the nearest cent. So all of these values here mean pretty much nothing or very little. We don't need those values. So I'm going to round. So that means because we have a 5 here, I'm going to round this up. So really, gold is going to be worth $3,017.04. So that's going to be the cost in 2005. So now I want to find the cost in 2015. So in 2015, that's going to be 15 years later. So the same idea. So I'm going to do y equals 1,500, 1.15. After 15 years that it compounds. All right, so that's going to give us a y value cost of 12,200. That's not a 2. 205,59,244. All right, so once again, these decimal values are nothing. We can't use them. So because we have a 2, we don't round at all, so it just stays as 9. All right, so your value here, the new price or value is going to be 12,205.59. All right, so now I'm going to go on to the year 2020. So in the year 2020, that's 20 years later, so that's your new t value. So we're going to have 1,500 1.15 raised to the 20. So when you raise it to the 20th power, our value is now 24,549.80609. All right, so remember, we can only have the nearest cent. So because of the 6, that means we round up. So our price here is going to be $24,549.81. All right, so keep in mind, I'm doing this all by hand. I will show you how to do this on the calculator in just a second. All right, so now in the year 2050, did I already do blue? Yes, I did. Let's do orange. All right, so in the year 2050, 50 years have passed. So now we're looking at 1,500, 1.15 raised to the 50. So now if I raise it to the 50, I wish. So 1,625,486.162. All right, so because we have a 2 here, the 6 just stays. So after 50 years, the price of gold per ounce will be $1,625,486.16. All right, so this is if I'm doing it by hand. It's not terribly bad. It's just not very convenient. So, all right, now I'm going to show you how to do this on the Casio. Okay, so if you want to do it by hand on Run Matrix, you can. So you can do 1,500 1.15, and then you can raise it to each value. So to the 0 power, that's what you get. If I do the 5th power, there's your next value, 1500, 1.15 raised to the, what was the next one? 15. So $12,205. So it works either way, whichever method that you want to do. So there's the next one, 5, and raised to the 20. So this is the issue. Oh, I did divide it by. Why am I like this? That's not right. There we go. So to the 20th, but I actually want 50. There we go. All right, so that's essentially what I just did. Now, if you also, nope, you also have the option of doing this in the table. So delete, goodbye. You can do 1,500, 1.15 raised to the x. Oh, shoot, I just realized. You can't type the letter x, you actually have to do the variable x. Otherwise, it will not compute. All right, then go to table. So this is good for the first few years. Like you can find it at 5 and at 10, 15. All right. Okay, so it does actually give you the decimal expansions. So you have to be careful with some of the decimal expansions here if you're using the table. So because I want all the way up to 50, go back to table. All right, so up to 15 was fine, but once it gets up to values such as, yeah, so right here, where you start seeing the E value, if you hover over that value, it'll give you the exact value. But on the table, you are not going to be able to just write 1.4 E6. Like you actually need to write out the value of the price of gold. All right. So just be careful with that when you're using the calculator. If the calculator is only giving you the exponentiated function or the exponentiated value, then you will have to go back to Run Matrix and just do it that way. All right. But yeah, you do have the option of using a calculator. So you don't have to do all these by hand. One thing I will say is whenever you're doing practices or whatever, you are going to be required to at least show your setup. So what you have to show is at least this part right here. All right. Okay. So number 2. So Quinn purchased a new 2021 Audi Q8 for $95,725. The rate of depreciation each year is approximately 18%. So one thing that's great about the exponential growth and decay, guys, is these are actually like authentic applications that happen in real life. So this is actually a great example of something that happens to real-time consumers in the market. So in a 2021 Audi Q8 for about $95,000, and the average rate of depreciation for vehicles can range anywhere from like 12 to like 25% per year. 25% is kind of steep. 12% is being a little generous, but a good average would be about 15 to 18%. All right, so does the scenario represent an exponential growth or decay? So because the value of the car is actually decreasing and it's losing value, it's going to be a decay. So the car is losing value. The car losing value. I can't English. The car is losing value over time. Everything's fine. I teach math for a reason. All right, so now we want to write an equation to model the scenario. So your initial retail price here, the 95K or approximately 96, this is going to be your A value. And then the rate of depreciation is 18%, which means your R value is 0.18. So I'm going to use this information to kind of write my equation. All right, so I know my equation here is going to be 95,725. Was it? Yes. And then it's losing value, so 1 minus 0.18 raised to the t. Now keep in mind, if it was gaining value, if it was actually increasing in value, then it would be plus. But because it's losing value, it's going to be minus. All right, so your equation here is going to be 95,000. That's not a 5. 95,725, then 0.82 raised to the t. So the actual vehicle here is only retaining 82% of its actual retail value each year. So every year it only carries over 82% of the value. So each year it's going to consistently, well, not consistently, it's going to consistently lose value, but eventually it's going to kind of bridge off and plateau. All right, so this is where the table in the calculator comes in real handy, because doing this by hand is such a pain. It's just time consuming. It's not difficult, it's just time consuming. So we want to find what will the car be worth after 5 years. Oh wait, this part's not bad. Oh, there we go. Part E. That's the part that's annoying to do by hand. All right, so we want to find what will the car be worth after 5 years. So this is essentially saying find f of 5. So I'm going to plug in 5. So this is going to be 96. I can't read, it's fine. 95, 725.82 raised to the 5th power. So after 5 years, so I'm just going to write out the full expansion first before I start doing any of the rounding. So 0.82 raised to the 5th. So when you plug it in after 5 years, the car is actually only going to be worth about $35,489 and 0.7149. So when I do my rounding to the nearest cent, it's only going to be worth $35,489. I can't read. Math is hard. English is hard. $35,489.07. So that is the car's worth after only 5 years. So it's lost more than half of its value in 5 years, the first 5 years. All right, so now we want to find the value of the car after 15 years. So once again, here, this is the same thing as saying find f of 15. All righty. So after 15 years, okay. So f of 15, so that's going to be 95,725.82 raised to the 15th. So when you plug it in, so the car after 15 years is only going to be worth approximately, well, let's write out the value first, $4,877.90301. So with rounding to the nearest cent, the car is only approximately worth $4,877.90. So for those of you curious about why the cars are only worth like $5 when you trade it in and try to buy a new car, you're like, what the heck? It's brand new, or it's not brand new. It's a great car. Why am I only getting $5? It's because the car is actually depreciating over time. So this is kind of how professionals actually appraise and calculate the worth of a car. All right, now for the fun one. I'm not gonna lie, I hate these problems anyways. Just this part. So after how many years will the car be worth less than 10K? So this is where I actually strategically do part C and D. We want to find when it's going to be less than 10K. So if you look, well, after 5 years, it's 35,000. And then after 10, nope, after 15, it's at about 5,000. So we know it's going to be between 5 and 15. So this is where I'm going to use the calculator because I'm not about that life. All right, so I actually did this on the note key, but for this, absolutely not. It's going to take forever. All right, so I'm going to plug in the equation. So 95,725.82 raised to the x. All right, I'm going to go to the table. I want to find when it's going to be less than 10K. So I want the Y1 column here to be 10K or less. All right, so the initial value is 95,725. So I'm going to keep going until that Y value reaches less than 10K. All right, so right here between year 11 and 12, it gets below 10K. So what you're going to say for your answer, you have a couple different options. You could say between 11 and 12 years, or you could just say after 11 years. So really, I would just say after 11 years is when it reaches below 10K, because it's not at 11 years, it's after 11 years. All right, so just to kind of put it in perspective, oh, Mike was doing this. All right, so let's do this way. I'll make a little makeshift table, but just for a few values, not for a lot of values. All right, so x is going to represent the number of years, whereas f of x represents the value. So let's say at 9, 10, 11, and 12. So at 9 years, it's worth 16,045.38. And then at 10 years, 13,157.1. After 11 years, it's at 10,788.91. Then at 12, it is 8,846.91. So we want it less than 10K. So here at 11 years, it's still higher than that threshold that we're looking for. But once it hits 12 years, it's finally below that 10K threshold that we're looking for. Hello, can we, oh my gosh. There we go. All right, so your final answer here is after 11 years. Or you could say between 11 and 12 years. So this is the algebra way to solve this. There's actually a calculus way to solve these using what we call natural logs and natural logarithms. You'll learn that later on. Don't worry about that now. But this is the algebra way to do it. When you get to the calculus way of doing it, it'll actually give you the exact time, like 11.4 whatever that you need. So in the meantime, we're just going to use the table. All right, so this next problem, for everyone wondering, how can I make free money? How can I get rich in the future? Or how could you save money for college? Or how could you save for retirement or whatever? Whatever big market amount that you need or a large amount of capital you need for whatever reason, whether it be buying a car, buying a house, saving for college, retirement, whatever. This is exactly how you want to do it. So Ryan opens up a money market account. So this is the key part right here. So this is actually a real life thing that you could do. So you could open a money market account at a bank and it's going to compound monthly at a certain percentage rate. So that's kind of the business side of things, but I would highly recommend doing a money market account if you can, because that's going to compound monthly and that's what's going to kind of give you free money as you get older. So anyways, you'll kind of see as we do the problem. All right, so Ryan opens up a money market account for his son Jake to start a college savings. So Ryan deposited an initial amount of $1,500 in the year 1994. So Jake graduates high school and enrolls in college in 2012. So the account compounds monthly at 2.25% with no monetary cap. So here's the thing about a money market account. The rates are not this high. The rates are typically below 1% in a real life money market account, but hey, that's still money that compounds that you get. And a lot of places actually do have a monetary cap. So for example, a bank I know of, the money market account actually compounds monthly at say 0.4%, and it only will compound up to a maximum monetary amount of 99K. So once it hits 99K, then it won't compound anymore. So just FYI. All right, so does this scenario represent an exponential growth or decay? Well, the value of the account balance is increasing, which means this is going to be a growth. The account is gaining money. So growth. The account balance so the account balance is increasing. All right, so now we want to model this situation with an equation. So you have to be careful how you write this, because the really extremely important part here in this problem is that it compounds monthly. That's the important part. So if I want to find it after a certain amount of years, then there's a certain equation. But if you want to find it in the account balance in a certain amount of months, that's a different equation. But they are similar. So if I want to find it in terms of months, then it's going to be 1 plus 0.0 225 to the t. So your equation here is going to be y equals 1,500, 1.0225 raised to the t. All right, so this is if I'm doing it per month. All right, so let's do this. So month. Now, if I want to do it per year, on a yearly basis, then that changes the exponent. So what that means is for a year, it's going to be 1.0225 raised to the 12t. So that's going to be per year. All right. Because after 5 years, you could find the value, but let's say you want to find 5 years and 3 months. If you want any component of the months, then you have to use the top equation. But if you want just after 7 years, 10 years, 20 years, then you can just use the bottom equation. Okay. All right. So assuming the money market account remains untouched and the interest rate stays the same, so they want to know how much money will be in the money market account in the year 2012. All right, so in the year 2012, you want to find out what your T value is going to be. So from 1994 to 2012, that is going to be 18 years. So we want to find the account balance after 18 years. All right, so since I'm just doing a yearly basis, then I'm going to use the bottom equation. Now, keep in mind, 18 years is going to be 216 months. So remember, you have to be careful which equation you're plugging it into, whether you're plugging it into the month equation or the year equation. All right, so I'm going to use the year equation. So I'm just going to copy and paste it down here. So I want it after 18 years. All right, so this is what I'm solving. So once again, actually do 1.0225. That's going to be raised to the 12 times 18. So after 18 years, this money market account, if it stays untouched with a 2.25% rate, in total, that account will have $183,386 with 63 cents. So keep in mind, just to kind of put this in perspective, in 1994, they started with 1,500. And after 18 years of just leaving it alone, letting it compound without contributing to it monthly, yearly, or whatever, it went all the way up to $183,000 in 18 years. So this is a really good way to kind of save money over time and kind of plan for any big purchase, especially like a house, apartment, whatever. Or if you want to start a business, this is also a really good way to do it. Okay, so now we're kind of analyzing the amount. So would Jake have enough money to attend the University of Texas in Austin in 2012 if a bachelor's degree cost $85,000? Well, he has $183,000 and the bachelor's here only costs $85,000. So yes, he would. You'd have more than enough. You can actually double major if you wanted to. All right. Would Jake have enough money to attend Vanderbilt University in 2012 if a bachelor's degree costs $200,000? Now, unfortunately, he's a little bit short. If he waits another year, then he probably would. But in 2012, he would not have enough. Unfortunately not. All right, so if Ryan doubled his initial investment in 1994, would he then have enough, or would Jake have enough to attend Vanderbilt at that time? So we're taking the initial equation. It's still like after 18 years. However, if he doubled the initial investment, then they want to see if he's going to have enough. So that's going to change to 3,000. All right, so if they doubled the investment, over here, my handy dandy little calculator. So after doubling the investment, they would have $366,000 and 773 cents. Nope, $773.25. So that'd be the balance after 18 years if you double the initial investment. So after doubling the initial investment, yes, they would. They would definitely have enough. So here's some applications for you guys to actually wonder, where the heck am I going to use this? Well, here you go. Money market account is your best bet. So those of you wanting to save up for college or save up for a house, retirement, whatever, open up a money market account and just leave it alone. Just let it compound.